Picture this standing on the surface of the Sun, where the heat is so intense, so unimaginable, that even the idea of it defies everything we know about survival. The air around you, if it could even be called air, would be a swirling chaos of superheated plasma, temperatures soaring to millions of degrees. In just a fraction of a second, every molecule in your body would vanish, not just melted, but completely torn apart at the atomic level. This isn't science fiction, it's the raw, unfiltered reality of the universe's most extreme temperatures, a realm where the rules of physics as we know them bend and break under the weight of such unimaginable heat and cold. The universe is a place of extremes, and nowhere is that more apparent than in the staggering range of temperatures it hosts. From the fiery hearts of stars to the icy void of deep space, these extremes push the boundaries of what we thought possible. Imagine a place so cold that atoms nearly stop moving altogether, or so hot that matter itself becomes something entirely different, a soup of particles dancing at energies beyond comprehension. These aren't just numbers on a scale, they're windows into the most violent, beautiful, and mysterious processes shaping our cosmos, and that's exactly what we're about to explore. Over the course of this video, we'll journey through 30 mind-bending facts about the universe's most extreme temperatures, each one more astonishing than the last. We'll dive into the science behind these extremes, uncover how they shape everything from stars to black holes, and even reveal how scientists recreate these conditions right here on Earth. So buckle up, because we're about to venture into a world where the ordinary rules of heat and cold don't apply, where the universe reveals its most breathtaking and terrifying secrets. This isn't just a lesson in physics, it's a front-row ticket to the most extreme show in existence. Absolute zero, the coldest temperature possible in our universe, is a concept so extreme it defies our everyday experience. At -273.15 degrees Celsius, all molecular motion theoretically stops. No vibration, no heat, nothing but pure stillness. This isn't just cold, it's the complete absence of heat, a state where the fundamental particles of matter reach their lowest possible energy. The idea of absolute zero isn't just a curiosity, it's a cornerstone of quantum physics, revealing how matter behaves when stripped of all thermal energy. Scientists have come incredibly close to reaching this impossible chill. In labs around the world, researchers use lasers and magnetic fields to slow atoms to a near standstill, creating exotic states of matter like Bose-Einstein condensates. These bizarre substances form when atoms are cooled so much that they merge into a single quantum wave, acting more like a single superatom than individual particles. It's as if trillions of atoms suddenly move in perfect unison, defying classical physics. But here's the catch: no matter how advanced our technology, we can never truly reach absolute zero. The laws of thermodynamics forbid it, making this temperature the ultimate unreachable frontier. Every attempt to get closer only reveals new quirks of quantum behavior, like how particles can still retain a ghostly whisper of energy even in the deepest cold. This lingering energy, known as zero-point energy, means that even at the edge of absolute zero, the universe refuses to let matter fall completely silent. The pursuit of absolute zero has led to breakthroughs in superconductivity, quantum computing, and even our understanding of the fabric of space-time. It's a reminder that in the coldest corners of the cosmos, the rules of physics become stranger and more wondrous than we ever imagined. The Boomerang Nebula holds a chilling record. It's the coldest known place in the natural universe, dipping to an almost incomprehensible -272 degrees Celsius. That's just 1 degree warmer than absolute zero, making it even colder than the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. This cosmic deep freeze exists because of a dying star at the nebula's heart, one that's throwing off gas at breakneck speeds, stellar winds rushing outward at over 160,000 kilometers per hour expand so rapidly that they steal heat from the surrounding space, creating a refrigeration effect on an interstellar scale. What makes this nebula even more fascinating is its distinctive shape, twin lobes of ejected material that give it the appearance of a cosmic boomerang. This structure forms as the star's outflowing gas collides with older, slower-moving material, creating shock waves that sculpt the nebula into its eerie, symmetrical form. Unlike the chaotic clouds of most nebulae, the boomerang's crisp edges and near-perfect symmetry make it a standout in the cosmos, almost as if nature itself paused to craft something unnervingly precise. To grasp just how extreme this cold is, consider Earth's lowest recorded temperature, -89.2 degrees Celsius in Antarctica. That's practically tropical compared to the boomerang's deep freeze. Even in laboratory settings where scientists create ultra-cold conditions, matching the nebula's natural chill remains a monumental challenge. Yet out in the depths of space, this frigid expanse exists effortlessly, a reminder of how the universe operates on scales and intensities far beyond our earthly experience. The Boomerang Nebula doesn't just break records, it shatters our expectations about where and how such extreme cold can exist. It's a cosmic paradox, a place of breathtaking beauty where the violence of a dying star creates conditions so cold they defy imagination. And as the nebula continues to expand, its ghostly chill serves as a humbling reminder that the universe's extremes aren't just curiosities, they're fundamental forces shaping the very fabric of reality. Pluto's frozen surface hovers around -233 degrees Celsius, a temperature so low that even nitrogen, a gas we breathe here on Earth, freezes solid into vast plains of shimmering ice. Yet for all its bone-chilling cold, Pluto isn't the coldest place in our solar system. That honor, as we've seen, belongs to the Boomerang Nebula's unnatural depths. But how does this distant dwarf planet, once considered our solar system's ninth member, maintain such extreme cold while other objects in the Kuiper belt exhibit even more extreme conditions? The answer lies in Pluto's delicate dance with the Sun. At an average distance of nearly 6 billion kilometers, sunlight takes over 4 hours to reach this tiny world, arriving as little more than a faint glow. This scarce energy creates an environment where surface temperatures barely fluctuate, allowing layers of nitrogen, methane, and carbon monoxide ice to persist across much of the landscape. Unlike Earth's water ice, these exotic ices behave differently under Pluto's weak gravity, flowing like glaciers in slow motion, carving valleys over millennia, and even creating floating mountains of water ice that rise above softer nitrogen plains. Seasons on Pluto are measured in decades, with each pole spending over 100 Earth years in continuous darkness or sunlight. During its long winter, temperatures plunge even further as the thin atmosphere, mostly nitrogen with traces of methane and carbon monoxide, freezes out entirely, falling like snow onto the surface. When spring finally arrives, sunlight vaporizes these ices back into gas, creating a temporary atmosphere before the cycle repeats. This seasonal heartbeat makes Pluto one of the most dynamically changing worlds we've observed, a place where the ground itself breathes in cosmic rhythms. Compare this to Eris, another dwarf planet in the Kuiper belt. Though similar in size to Pluto, Eris orbits even farther from the Sun, so distant that its surface temperatures drop below -240 degrees Celsius. Without atmospheric seasons to moderate its climate, Eris remains locked in a deeper freeze, its surface likely coated in pristine ice untouched by the geological activity that reshapes Pluto. Meanwhile, smaller Kuiper belt objects like Makemake show patchy evidence of methane frosts, suggesting a complex interplay of chemistry and temperature across these frozen worlds. What makes Pluto truly special isn't just its cold, it's how this cold interacts with every facet of its existence. From ice volcanoes spewing frozen slurries to drifting haze particles that paint its skies blue at sunrise, Pluto's extreme temperatures don't create a dead world but an unexpectedly vibrant one. Every New Horizons image reveals new mysteries. Why do some regions look like dragon scales while others resemble frozen lava lamps? How does its atmosphere persist when similar-sized worlds lose theirs? Each question reminds us that in the outer solar system, cold isn't just an absence of heat. It's an architect carving alien landscapes where the rules of Earth no longer apply. Beneath Europa's cracked and frozen shell, where surface temperatures plunge to -220 degrees Celsius, lies one of the solar system's greatest mysteries, a global ocean kept liquid against all odds. This moon of Jupiter, no larger than Earth's own, shouldn't have any business hosting liquid water. At such distances from the Sun, worlds typically freeze solid. Yet Europa defies expectations, its icy surface crisscrossed with reddish streaks and chaotic terrain, hinting at the churning waters below. The secret to this paradox lies in Jupiter's immense gravitational pull. As Europa orbits, the gas giant's tidal forces stretch and squeeze the moon's interior, creating friction that generates heat, a process called tidal heating. Imagine repeatedly bending a paperclip until it grows warm to the touch. Now scale that up to planetary proportions with an entire moon flexing under gravitational stress. This internal warmth acts like a cosmic furnace, preventing Europa's subsurface ocean from freezing despite the crushing cold just kilometers above. Evidence for this hidden sea is everywhere. The moon's surface resembles a cracked eggshell, with vast ice plains giving way to ridges and fractures where material from below appears to have welled up and refrozen. Dark, rusty-hued compounds, possibly salts or organic molecules, streak across the landscape, staining the ice where it's been exposed to space. Most telling are the plumes of water vapor that occasionally erupt from Europa's south pole, spotted by telescopes and spacecraft alike. These geysers briefly breach the icy crust, offering a tantalizing taste of what might lurk in the darkness below. But how thick is this icy barrier? Estimates vary, with some suggesting it could be as little as a few kilometers in certain regions, while others propose a shell dozens of kilometers thick. The variations likely depend on local geology. Areas where the ice is thinner might experience more frequent cracking, allowing subsurface material to reach the surface. This dynamic process creates a landscape in constant flux, where fresh ice smooths over old fractures even as new ones form. What makes Europa especially compelling is the possibility that its ocean could harbor life. On Earth, ecosystems thrive around hydrothermal vents in the deepest, darkest parts of our oceans, far from sunlight. If similar vents exist on Europa's seafloor, warmed by tidal forces and mineral rich from interactions with the rocky mantle, who's to say life couldn't take hold there too? The chemicals staining Europa's surface might be the fingerprints of a hidden biosphere waiting to be discovered. Upcoming missions like NASA Europa Clipper aim to answer these questions, skimming just 25 kilometers above the surface to study its composition in unprecedented detail. Future landers might one day drill or melt through the ice, sending probes into the abyss below. Until then, Europa remains a world of extremes, a place where unimaginable cold meets hidden warmth, creating an environment unlike any other in our solar system. It's a reminder that even in the most hostile corners of space, nature finds a way to surprise us. Mars' polar caps are a study in extremes, where temperatures plummet to -125 degrees Celsius, cold enough to freeze carbon dioxide straight out of the thin Martian atmosphere. Unlike Earth's poles, where water ice dominates, these frozen regions are a mix of water ice and thick layers of carbon dioxide ice, also known as dry ice. During winter, nearly 30% of the planet's entire atmosphere freezes onto these caps, creating a surreal landscape where snowflakes aren't made of water, but of carbon dioxide crystals. The scale of these ice formations is staggering. The northern polar cap spans over 1,000 kilometers across, with layered deposits of ice and dust stacked several kilometers high, like a frozen history book recording millions of years of Martian climate cycles. In contrast, the southern cap is smaller but even colder, with some areas remaining covered in dry ice year-round. These caps aren't static, they breathe with the seasons. As temperatures rise, carbon dioxide sublimates directly from solid to gas, creating fierce winds that sweep dust across the planet, sometimes triggering global dust storms capable of shrouding Mars for months. Rovers like NASA, Phoenix, and Perseverance have taken the planet's temperature firsthand, revealing just how wildly conditions fluctuate. During winter nights, the surface can drop to -130 degrees Celsius near the poles, but daytime temperatures can climb to a relatively balmy -20 degrees Celsius in sunlit areas. These swings aren't just numbers, they shape everything from the way ice cracks and reforms to the bizarre phenomenon of spiders, intricate patterns carved into the ground as trapped carbon dioxide gas erupts from beneath the ice in spring. The dust storms that rage across Mars add another layer of complexity. These tempests don't just obscure the surface, they dramatically alter temperatures. As dust fills the atmosphere, it traps heat like a blanket, causing polar regions to warm temporarily while equatorial zones cool. It's a climatic seesaw unlike anything on Earth, where storms can reshape the entire planet's thermal balance in weeks. What makes Mars' cold truly unique isn't just the raw temperatures. It's how this cold interacts with the planet's thin atmosphere and alien chemistry. On Earth, ice melts into water. On Mars, dry ice skips the liquid phase entirely, vanishing into gas and leaving behind Swiss cheese-like terrain riddled with pits and fans of ejected dust. Even the ice itself behaves differently. Martian water ice is so cold that it's harder than steel, flowing in slow, glacial movements over millennia without melting. These poles aren't just frozen wastelands, they're dynamic engines driving Mars' climate, archives of its past, and perhaps even reservoirs for future explorers. Scientists suspect that beneath the ice, briny liquid water might lurk in pockets, kept liquid by salts that lower its freezing point. If true, it would mean that even in the deepest cold, Mars still holds secrets that could rewrite our understanding of habitability beyond Earth. On July 21, 1983, scientists at Antarctica's Vostok station recorded a temperature that would rewrite climate history, -89.2 degrees Celsius, the coldest natural temperature ever measured on Earth. At these extremes, breath instantly freezes in the air, metal becomes brittle enough to shatter, and exposed skin suffers frostbite in mere minutes. Yet what makes this record even more astonishing is how such brutal cold emerges in Earth's otherwise temperate climate system. Vostok Station sits atop the East Antarctic ice sheet, nearly 3.5 kilometers above sea level on one of the most isolated plateaus on the planet. Three critical factors converge here to create these record lows. First, the elevation, thin air holds less heat, allowing rapid cooling. Second, Antarctica's winter polar night lasts for months, depriving the surface of sunlight that could provide even minimal warmth. Finally, the ice sheet itself acts like a colossal mirror, reflecting over 90% of incoming solar radiation back into space instead of absorbing it. But the real secret lies in the weather patterns that lock this cold in place. For days before the record measurement, a high-pressure system hovered over Vostok, creating what scientists call a radiation inversion. Normally, air gets colder with altitude, but during an inversion, dense cold air sinks and pools near the surface like an invisible lake, trapped under a lid of slightly warmer air above. Without wind to mix these layers, the ground-level air keeps cooling relentlessly, degree by impossible degree. Miraculously, life persists even here. Microbes known as psychrophiles thrive in Vostok's ice, their cellular structures adapted to prevent freezing through natural antifreeze proteins. Nearby, in subglacial lakes sealed beneath 4 kilometers of ice, entire ecosystems may flourish in permanent darkness, warmed faintly by geothermal heat and sustained by chemistry alone. Even visible life endures. Tiny arthropods called springtails hop across the snow during brief summer thaws, surviving winters in suspended animation. The cold plays tricks on perception too. At these temperatures, sound behaves differently. Voices carry farther as cold air's density transmits vibrations more efficiently, while footsteps crunch with an unnaturally crisp clarity. Exhaled breath instantly crystallizes into a cloud of ice particles, and if you pour boiling water into the air, it vaporizes before hitting the ground in a spectacular frozen mist. What makes Vostok's record truly humbling is how fleeting such extremes are on a cosmic scale. While impressive by Earth standards, it's still over 180 degrees warmer than Pluto's surface and nearly 400 degrees warmer than the Boomerang Nebula. Yet this delicate balance, just cold enough to push life to its limits, but not so cold as to erase it completely, shows how even Earth's most hostile corners remain improbably vibrant compared to the true deep freeze of space. Liquid nitrogen exists in a strange middle ground between the everyday and the extreme at -196 degrees Celsius. It's cold enough to instantly freeze organic matter, yet common enough to be used in everything from medicine to gourmet cooking. Watching it pour out of its container is like witnessing a witch's cauldron in reverse, the liquid boiling furiously at room temperature as it vaporizes into dense, flowing fog. This surreal substance bridges the gap between laboratory curiosity and practical tool, with applications that range from the life-saving to the downright theatrical. Dunk a rose into liquid nitrogen, and in seconds it transforms into something resembling delicate glass. The water inside its cells freezes so rapidly that the petals become brittle enough to shatter with a touch, demonstrating how extreme cold can rewrite the rules of biology. Bananas take on new properties too frozen solid. They can drive nails through wood like tiny hammers, their cellular structure locked in place by the sudden deep freeze. These dramatic demonstrations aren't just party tricks, they reveal fundamental truths about how materials behave at cryogenic temperatures, where flexibility gives way to fragility. Beyond the spectacle, liquid nitrogen plays critical roles across industries. In medicine, it's the backbone of cryosurgery, where precise application destroys abnormal tissue by flash freezing it. Dermatologists use it to remove warts, while cancer specialists employ it to target tumors without invasive cuts. The food industry relies on it for everything from instantly freezing premium seafood to creating ultra-smooth ice creams with microscopic ice crystals. Even tech companies use it to stress test electronics, ensuring devices can withstand accidental exposure to extreme cold. Perhaps its most fascinating application lies in fertility clinics, where liquid nitrogen preserves eggs, sperm, and embryos in suspended animation. Stored in specialized tanks, these biological materials can remain viable for decades, their molecular activity nearly halted by temperatures colder than the surface of Pluto. It's a testament to how humanity has harnessed extreme cold not just for destruction, but for preservation, turning what should be lethal into a tool for creating life. Handling liquid nitrogen comes with sobering risks. Its extreme cold can cause severe frostbite in seconds, and if sealed in a container, vaporizing nitrogen can build explosive pressure. One famous demonstration filling a plastic bottle with liquid nitrogen and capping it shows how rapidly expanding gas can launch the container like a rocket, a vivid lesson in phase transitions and gas laws. These dangers demand respect, but they also make nitrogen one of science's most compelling teaching tools, offering immediate, visceral lessons in thermodynamics that no textbook could match. What makes liquid nitrogen truly remarkable isn't just its temperature, it's how something so alien has become woven into the fabric of modern life. From the operating room to the kitchen, from research labs to art installations where fog spills across stages like ghostly rivers, this ultra-cold liquid reminds us that the universe's extremes aren't always light years away. Sometimes they're right there in a dew-or flask, bubbling quietly, waiting to reveal the extraordinary physics hiding just beneath the surface of our ordinary world. Superconductors defy everything we know about electricity, achieving what seems like magic, the complete absence of resistance. At ordinary temperatures, electrons bump and scatter through wires, wasting energy as heat. But cool certain materials to their critical temperature, and this chaos transforms into perfect order. Electrons pair up and glide effortlessly, as if the materials suddenly forgot how to slow them down. Take yttrium barium copper oxide, or IBCO, a ceramic compound that becomes superconducting at -181 degrees Celsius. That's 80 degrees warmer than liquid nitrogen's boiling point, a relative heat wave in the world of extreme cold. This phenomenon isn't just lab curiosity, it's the key to revolutionizing energy. Imagine power grids with zero loss, where electricity generated at a solar farm travels thousands of kilometers without wasting a single watt. Or MRI machines so efficient they require no liquid helium, making medical diagnostics cheaper and more accessible. Even maglev trains, floating silently over tracks at 500 kilometers per hour, rely on superconducting magnets to achieve frictionless motion. The catch: maintaining these ultra-cold temperatures demands constant energy, creating a paradox where we spend power to save power. The quest for higher critical temperatures has become a scientific marathon. Mercury-based superconductors discovered in the early 20th century required cooling to -269 degrees Celsius within a few degrees of absolute zero. Then came the high-temperature superconductors of the 1980s, like IBCO, which shattered expectations by working at comparatively balmy -180 degrees. Recently, hydrogen sulfide shocked researchers by superconducting at -70 degrees under extreme pressure, hinting at a future where these materials might operate in ordinary freezers rather than specialized cryogenic chambers. What makes superconductivity even stranger is the Meissner effect, a superconductor's ability to expel magnetic fields entirely, causing magnets to levitate above them as if defying gravity. This isn't just a party trick, it's proof of quantum physics operating on a visible scale. The effect enables ultra-precise sensors used in everything from brain imaging to mineral exploration, detecting magnetic fluctuations 1 billion times weaker than Earth's field. Yet for all their promise, superconductors remain finicky. Even the slightest impurity or misalignment in their crystal structure can destroy their perfect conductivity. Some require such precise oxygen content that synthesizing them resembles alchemy as much as materials science. And while theorists predict room temperature superconductors might exist, actually finding one has become the field's holy grail, a discovery that could upend energy infrastructure overnight. The true marvel isn't just that superconductors exist, but that they reveal how extreme cold can unlock entirely new states of matter. In a universe where heat dominates, these materials remind us that profound transformations happen when we push temperatures to the edge of impossibility. Every flicker of superconducting current is a glimpse into a world where electrons dance in perfect harmony, unburdened by resistance, a silent revolution waiting in the cold. Inside a nondescript lab at MIT, physicists have created the coldest spot in the known universe, a chilling -273.144 degrees Celsius, just a whisper above absolute zero. To grasp how extreme this is, consider that deep space itself hovers around -270, making this lab over 10,000 times colder than the cosmic background radiation bathing the entire universe. Achieving such staggering cold isn't about brute force cooling, it's an intricate ballet of quantum manipulation, where scientists don't just lower temperature but fundamentally rewrite how atoms behave. The secret lies in laser cooling, a counterintuitive technique that turns light into a kind of atomic refrigeration. picture billions of rubidium atoms floating in a vacuum chamber. Researchers bombard them with precisely tuned lasers from all directions, their photons acting like tiny punches to slow the atom's motion. It's as if you tried to stop a rolling bowling ball by pelting it with ping-pong balls. Each impact steals a fraction of the atom's energy, gradually bringing its frenetic dance to a near standstill. At these temperatures, atoms move slower than a crawling snail, covering mere millimeters in an entire second. But lasers alone can't reach the coldest extremes. Enter magnetic trapping, a way to corral these sluggish atoms without physical contact. Superconducting coils generate magnetic fields so precise they create invisible bowls in space where atoms collect like marbles in a dimple. The real magic happens when researchers adjust these fields to selectively let the warmest atoms escape, leaving only the coldest behind. This evaporative cooling mirrors how your morning coffee cools as steam carries away heat, but here it's applied to individual atoms at temperatures where quantum weirdness takes over. Why push these limits? Because at these temperatures, matter reveals its quantum soul. Atoms lose their individuality, merging into a single quantum wave called a Bose-Einstein condensate, a state where particles move in eerie synchrony like a cosmic flash mob. This isn't just laboratory spectacle, it's a portal to new technologies, super-accurate atomic clocks, quantum computers that harness these strange states for calculation, and sensors so sensitive they could detect the gravitational waves from distant supernova all depend on mastering ultra-cold matter. Yet the coldest lab on Earth isn't just about breaking records, it's a proving ground for understanding how the universe behaves at its most fundamental level. The same quantum rules governing these frigid atoms may one day explain dark matter or the fabric of space-time itself, and every fraction of a degree closer to absolute zero peels back another layer of reality, revealing a world where the ordinary laws of physics surrender to something far more mysterious. Even in the emptiest reaches of space, far from any star or galaxy, the universe isn't truly dark or cold, it's bathed in the faint glow of creation itself. This is the cosmic microwave background, or CMB, a thermal echo of the Big Bang that has cooled to just 2.7 degrees above absolute zero, minus 270.4 degrees Celsius. It's the oldest light we can detect, emitted when the universe was a mere 380,000 years old, and now stretched by cosmic expansion into microwave wavelengths that whisper across the void. The discovery of this background radiation in 1964 was like finding the universe's birth certificate. Two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon it while troubleshooting persistent static in their antenna, a hiss that came from every direction no matter where they pointed. At first, they blamed pigeon droppings on their equipment, but after meticulous cleaning, the signal remained, revealing itself as the cooled remnant of the primordial fireball that birthed everything we know. What makes the CMB so remarkable is its near-perfect uniformity, varying by only microscopic fluctuations, 1 part in 100,000. These tiny wrinkles in temperature, mapped in exquisite detail by satellites like COBE and Planck, are the seeds of all cosmic structure. Slightly denser regions pulled in more matter through gravity, eventually growing into galaxies and galaxy clusters. It's as if we're looking at the universe's blueprint, frozen in microwaves that have traveled for over 13 billion years to reach us. Yet this cold glow holds even deeper mysteries. Its precise temperature reveals the universe's geometry, flat within a fraction of a percent, while its polarization patterns hint at gravitational waves from the universe's first trillionth of a second. Some theories suggest the CMB might even bear scars from collisions with other universes in a vast multiverse. Every new measurement peels back another layer, from confirming dark energy's existence to challenging our understanding of cosmic inflation. Unlike the Boomerang Nebula's localized chill or Pluto's icy plains, the CMB's cold is everywhere, a fundamental temperature flaw woven into the fabric of space-time. It's the ultimate baseline against which all other cosmic temperatures are measured, proof that even in the deepest void, the universe still carries the memory of its fiery origins. And as the cosmos continues expanding, this afterglow will grow colder still, fading but never vanishing, a perpetual reminder that every empty space is anything but empty. Mercury presents one of the solar system's most dramatic temperature swings, a world where the sunlit side roasts at 430 degrees Celsius, hot enough to melt lead, while the night side plunges to -173 degrees, colder than Earth's polar winters. This extreme contrast isn't just a curiosity, it's a direct consequence of Mercury's near-total lack of atmosphere. Without an insulating blanket of gases to trap or distribute heat, temperatures fluctuate wildly between day and night, creating a planet of two brutally opposite faces. NASA Messenger spacecraft, which orbited Mercury from 2011 to 2015, mapped these extremes in unprecedented detail. Its instruments revealed how quickly heat vanishes when the sun sets, like opening a cosmic freezer door. On Earth, our atmosphere acts like a thermal sponge, absorbing warmth during the day and gradually releasing it at night. But Mercury's wispy exosphere, thinner than the best vacuum we can create in labs, offers no such buffer. Sunlight bakes the surface unimpeded, and as soon as that light disappears, heat radiates into space almost instantly. The data showed something even stranger. Regions near Mercury's poles, permanently shadowed inside deep craters, never warm up at all. These frozen pockets harbor water ice, a discovery that stunned scientists. How could a planet so close to the sun, where surface temperatures could boil water during the day, preserve ice? The answer lies in Mercury's minimal axial tilt. Unlike Earth, whose poles tilt toward and away from the sun seasonally, Mercury's rotation is nearly perpendicular to its orbit. This geometry creates crater floors that sunlight never reaches, cold traps where ice survives for billions of years despite the surrounding inferno. Messenger thermal measurements also uncovered Mercury's hot poles, areas just beyond the terminator line where daytime heat lingers slightly longer. These transitional zones experience some of the most rapid temperature changes ever recorded in the solar system, shifting hundreds of degrees in minutes as the planet's slow rotation, one day lasts 59 Earth days, drags regions in and out of sunlight. What makes Mercury's cold side especially fascinating is how it challenges our assumptions about planetary climates. Even on worlds closer to the sun than Earth, shadows can be colder than Pluto. This duality, a surface simultaneously hosting scorching deserts and deep freezes, reveals how much a planet's personality depends on factors beyond just distance from its star. Atmosphere, rotation, and even topography conspire to create environments more nuanced than we ever imagined. Future missions, like the joint European-Japanese Bepi Colombo probe now orbiting Mercury, aim to explore these extremes further. By studying how heat flows across the planet's surface, scientists hope to unlock secrets not just about Mercury, but about how all rocky worlds balance their temperatures or fail to. After all, in a universe where a single planet can be both furnace and icebox, the line between habitable and hostile is thinner than we thought. Titan, Saturn's largest moon, hides a surreal secret beneath its thick orange haze, vast lakes and rivers not of water, but of liquid methane, flowing at a frigid -179 degrees Celsius. This moon is the only place in the solar system besides Earth with stable liquid bodies on its surface, though the chemistry here is utterly alien. Imagine standing on Titan's shoreline, watching methane waves lap against icy pebbles under a dim, smoggy sky. The breeze wouldn't rustle leaves, it would carry droplets of liquid natural gas, chilling everything it touches into a brittle, frozen state. The Cassini spacecraft, which orbited Saturn for 13 years, peeled back Titan's mysteries with radar and infrared eyes. Its observations revealed lakes as deep as 100 meters, some spanning hundreds of kilometers across, equivalent in size to North America's Great Lakes. These aren't stagnant pools. Cassini spotted shifting shorelines and islands that appeared and vanished, hinting at dynamic tides driven by Saturn's gravity or even seasonal methane rainfall. The largest sea, Kraken Mare, holds enough liquid methane to fill Lake Michigan 11 times over, an astonishing volume of hydrocarbons sloshing in slow motion under reduced gravity. Even stranger are the cryovolcanoes that might dot Titan's landscape. Instead of spewing molten rock, these icy vents could erupt a slurry of water, ammonia, and methane, a geological phenomenon unlike anything on Earth. When Cassini detected transient bright spots on Titan's surface, some scientists theorized they were witnessing cryovolcanic activity, where subsurface lava of slushy ice oozes out before freezing solid in the moon's bitter cold. These eruptions might replenish Titan's atmosphere with methane, solving a long-standing puzzle. Why hasn't all the moon's methane been broken down by sunlight over billions of years? The methane cycle on Titan mirrors Earth's water cycle with eerie precision. Evaporation forms clouds which condense into rain, carving valleys and filling lakes, except here, the raindrops fall at a languid pace, taking minutes to reach the ground due to Titan's thick atmosphere and low gravity. During Cassini's mission, it captured images of methane storms dousing equatorial regions, then watched as the resulting streams evaporated within weeks. A sped-up version of Earth's hydrological cycle played out with alien chemistry. What makes Titan's cold so remarkable isn't just the temperature, it's how this cold enables chemistry that would be impossible on warmer worlds. At these extremes, methane behaves like water, while water ice becomes as hard as granite, forming mountain ranges and riverbeds. Organic molecules raining from the sky collect in the lakes, creating a primordial soup that some astrobiologists believe could mirror Earth's conditions before life emerged. Future missions like NASA's Dragonfly, a rotorcraft set to explore Titan in the 2030s, will search for these probiotic ingredients among the moon's dunes and icy plains. Titan challenges our definitions of habitability. It's a world where life as we know it couldn't survive, yet one that simulates Earth's processes with uncanny accuracy, a reminder that nature's playbook is far more versatile than we ever imagined. Whether through cryovolcanoes rewriting surface features or methane tides shaping shorelines, this moon proves that even in the deepest cold, planetary worlds remain astonishingly alive. Venus wears its extremes like a cosmic paradox, a planet where the surface bakes at 460 degrees Celsius, hot enough to melt lead, yet just 60 kilometers up, temperatures in its upper clouds plummet to a surprising -70 degrees. This dramatic shift turns our usual understanding of planetary atmospheres upside down. On Earth, we expect higher altitudes to bring colder air, but Venus takes this concept to an almost deceptive extreme, crafting an environment where the difference between cloud tops and surface rivals the span between a volcano's heart and Antarctica's deepest ice. The secret lies in Venus's thick blanket of sulfuric acid clouds. These aren't the fluffy water vapor formations we know. They're a corrosive, high-altitude haze stretching 30 to 60 kilometers above the surface, reflecting most sunlight before it can penetrate deeper. Like a planetary sunshade, these clouds prevent heat from reaching the upper layers while trapping it below in a runaway greenhouse effect. Sunlight that does filter through interacts with sulfur dioxide and other compounds, creating a photochemical smog that absorbs and scatters energy in ways Earth's atmosphere never could. The result, a thermal inversion so sharp it carves Venus's climate into distinct chapters, a broiling hellscape below and a frigid, windswept expanse above. Probes like ESA's Venus Express have mapped these layers in detail, revealing jet streams in the upper atmosphere that scream past at 300 kilometers per hour, 6 times faster than Venus's sluggish surface rotation. At these altitudes, the cold isn't just a curiosity, it shapes bizarre chemistry. Sulfuric acid droplets freeze into ice crystals despite the acidic environment, creating reflective veils that make Venus the solar system's shiniest planet when viewed from afar. Meanwhile, trace water vapor gets locked into hyper-concentrated acid aerosols, forming a global layer so corrosive it would devour most spacecraft instruments within hours. What makes this cold zone truly startling is how it defies expectations about Venus's evolution. Early astronomers once imagined the planet as a tropical twin of Earth, but we now know its atmosphere underwent a catastrophic transformation. Billions of years ago, volcanic outgassing may have flooded the skies with sulfur, triggering feedback loops that dried up oceans and baked the surface while leaving the upper atmosphere isolated and icy. The contrast between these layers isn't just weather. It's a planetary-scale cautionary tale about how delicate climate balance can be. Future missions like NASA Da Vinci Plus aim to unravel this mystery by descending through Venus's atmosphere, sampling its chemistry like a cosmic sommelier. As the probe plunges from frigid clouds into infernal depths, it'll document a thermal gradient no terrestrial organism could survive, a reminder that temperature extremes aren't just numbers on a scale, but forces that rewrite the very definition of a world. Venus teaches us that even in the harshest environments, nature finds ways to surprise, proving that a planet's story can't be told by its surface alone. Neutron stars are the cosmic equivalent of a diamond forged in a nuclear furnace, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. But it's their surface temperatures that defy comprehension. A blistering 1 million degrees Celsius, hot enough to vaporize any known substance instantly. These extreme temperatures aren't just a byproduct of their formation, they're a direct consequence of the star's violent death and mind-bending physics. When a massive star explodes as a supernova, its core collapses under unimaginable pressure. Protons and electrons get crushed together, forming neutrons in a process so energetic that temperatures briefly spike to 100 billion degrees hotter than the center of the Sun at its peak. The resulting neutron star, barely 20 kilometers across, retains this ferocious heat, its surface glowing with X-rays visible across interstellar distances. Compare that to the supernova explosion itself, which reaches even more extreme temperatures around 10 billion degrees, but only for a fleeting moment before dissipating into space. The neutron star, by contrast, keeps its million-degree surface for millennia, a simmering remnant of cosmic violence. What makes these temperatures even more astonishing is how they're maintained. Unlike stars which generate heat through ongoing nuclear fusion, neutron stars slowly cool over time. Their surfaces stay scorching due to two main factors: residual heat from the initial collapse and the decay of unstable particles in their cores. Some neutron stars, called magnetars, have magnetic fields so intense they generate additional heating through quantum effects, twisting the star's crust and releasing bursts of energy that can temporarily make the surface even hotter. The practical effects of this heat are mind-bending. If you could somehow hover near a neutron star's surface, ignoring the lethal radiation and gravity that would flatten you into a subatomic smear, the thermal radiation alone would vaporize any spacecraft instantly. Even from light years away, the X-rays emitted by these surfaces are detectable, a beacon of extreme physics that helps astronomers study matter under conditions impossible to recreate on Earth. Some neutron stars in binary systems steal material from companion stars, creating accretion disks that spiral inward and heat up further, generating X-ray flares that outshine entire galaxies for brief, spectacular moments. Yet for all their ferocious heat, neutron stars aren't the hottest objects in the universe. That honor likely goes to quark stars or the interiors of active galactic nuclei. What makes neutron stars special is how they balance extremes: unimaginable density paired with equally unfathomable heat, all packed into a city-sized sphere spinning faster than a kitchen blender. They're nature's ultimate pressure cookers, where the rules of thermodynamics get rewritten daily, and where even the concept of surface takes on a meaning stranger than science fiction. The Sun holds one of the most baffling temperature paradoxes in our solar system. Its wispy outer atmosphere, called the corona, burns at a staggering 1 to 3 million degrees Celsius, while the visible surface below simmers at a relatively cool 5,500 degrees. This defies all common sense. Usually, temperatures drop as you move away from a heat source, not soar to incomprehensible heights. Imagine standing near a campfire and feeling the air 10 meters away suddenly become 50 times hotter than the flames themselves. That's the level of cosmic strangeness we're dealing with here. At the heart of this mystery lies the Sun's tangled magnetic field. Unlike Earth's relatively orderly field, the Sun's magnetism is chaotic, with loops and arcs constantly twisting, snapping, and reconnecting in a process called magnetic reconnection. When these field lines break and reform, they release colossal amounts of energy like rubber bands stretched to their limits and suddenly cut. This energy pumps heat into the corona, supercharging it to temperatures that dwarf the Sun's surface. NASA Parker Solar Probe, which flies closer to the Sun than any previous spacecraft, has observed these explosive events firsthand, detecting bursts of energy that match theoretical predictions almost perfectly. But reconnection isn't the only suspect. Another theory points to solar waves, ripples in the Sun's plasma that carry energy outward like ocean waves crashing onto a beach. Some of these waves, particularly Alfvén waves, might dump their energy into the corona instead of dissipating, acting like a continuous heat injection. There's also nanoflare theory, which suggests that countless tiny explosions, each too small to detect individually, collectively deliver enough energy to explain the corona's extreme heat. The corona's heat has real consequences beyond scientific curiosity. This superheated plasma escapes as the solar wind, a stream of charged particles that races toward Earth at 1,000,000 miles per hour. Without our planet's magnetic field shielding us, this wind would strip away our atmosphere. Coronal heating also drives space weather, which can disrupt satellites, knock out power grids, and even pose radiation risks to astronauts. Understanding the corona isn't just about solving a physics puzzle, it's about protecting our increasingly technological civilization from the Sun's fiery temper. What makes this enigma even more fascinating is how it connects to other stars. If we can crack the code of our own Sun's corona, we might unlock universal principles governing stellar atmospheres across the galaxy. Telescopes have spotted similarly scorching coronas around distant stars, suggesting this isn't just a solar fluke but a fundamental process woven into the fabric of the cosmos. The Sun, in all its fiery glory, is giving us front-row seats to one of nature's great performances, a show where magnetism, plasma, and raw energy collide in ways we're only beginning to understand. Lightning transforms the sky into a natural particle accelerator, reaching temperatures of 30,000 degrees Celsius, 5 times hotter than the surface of the Sun. But unlike the Sun's steady nuclear furnace, this extreme heat lasts for mere microseconds, a fleeting burst of energy so intense it tears electrons from air molecules, creating a channel of superheated plasma. What we see as a brilliant flash is actually atoms being ripped apart and reassembled in a chaotic dance, a process that releases enough energy to power a small town for minutes, all compressed into a strike shorter than the blink of an eye. The physics behind this phenomenon is as elegant as it is violent. As electrons race downward in a stepped leader, they superheat the air to nearly 30,000 degrees, causing it to glow with the same blue-white intensity as welding torches. When this conductive path completes its circuit with the ground, the return stroke unleashes the visible lightning bolt, essentially a massive electrical short circuit through the atmosphere. The surrounding air, now a plasma, expands explosively, creating the shockwave we hear as thunder. this isn't just noise, it's the sound of the atmosphere itself being torn open and slamming back together, a sonic footprint of the lightning's energy dispersal. What makes lightning's heat even more astonishing is its contrast with the sun. While the sun's surface simmers at a mere 5,500 degrees, its heat is sustained by continuous fusion reactions. Lightning achieves higher temperatures through sheer electrical violence, like comparing a blast furnace to the instantaneous flare of a detonating firework. Yet for all its intensity, this heat evaporates almost instantly because the plasma channel is too narrow to retain energy. The surrounding cold air rushes in, quenching the reaction before it can linger, a self-limiting inferno that prevents our atmosphere from becoming a permanent furnace. Thunder plays a crucial role in balancing this energy. The rumbles and cracks aren't just byproducts, they're the atmosphere's way of redistributing the lightning's shockwave energy safely across miles. High-frequency thunder cracks indicate nearby strikes where energy hasn't had time to disperse, while low, rolling booms come from distant strikes where sound waves have bounced between layers of warm and cold air, stretching the energy over seconds. This natural damping system ensures that even the most violent lightning strikes don't overwhelm the environment with concentrated heat. Scientists harness these principles in plasma labs, where artificial lightning helps study materials under extreme conditions or even triggers nuclear fusion experiments. Meanwhile, lightning's ephemeral heat leaves behind forensic clues: fulgurite, the glassy tubes formed when sand is fused by strikes, and Lichtenberg figures, the fractal-like burns sometimes etched into survivors' skin. These traces remind us that for all its brevity, lightning's touch etches itself into the world in ways both destructive and wondrous. In the grand spectrum of cosmic temperatures, lightning stands apart, not for its duration, but for its ability to compress the energy of stars into a split-second spectacle. Deep beneath our feet, Earth's core simmers at a staggering 6,000 degrees Celsius hotter than the surface of the Sun. This isn't leftover heat from the planet's formation billions of years ago. It's an ongoing nuclear furnace fueled by radioactive decay. Elements like uranium, thorium, and potassium deep within the mantle and core release energy as they break down, acting like slow-burning atomic batteries. Combine that with the crushing pressure over 3.5 million times what we experience at sea level, and you have a thermal engine that's kept our planet's interior molten for eons. This extreme heat doesn't just sit idle, it powers the conveyor belts of plate tectonics. The mantle, heated from below, churns in slow motion, dragging continents apart at mid-ocean ridges and shoving them together at subduction zones. Without this internal fire, Earth would be as geologically dead as Mars, its surface frozen in time. Volcanic eruptions, earthquakes, even the recycling of minerals that sustains life, all trace back to the core's relentless output. But perhaps the core's greatest gift is Earth's magnetic field. As molten iron swirls around the solid inner core, it generates electric currents through the dynamo effect. These currents produce a protective magnetic shield stretching thousands of kilometers into space, deflecting the solar wind's lethal radiation. Without this invisible force field, our atmosphere would have been stripped away eons ago, leaving Earth as barren as Mars. Curiously, this system isn't perfectly stable. The magnetic North Pole drifts unpredictably, and historical records show the field's strength fluctuates, sometimes weakening enough to flip polarity entirely. During these transitions, which take thousands of years, Earth's protection against cosmic rays diminishes. Geologists have found evidence linking past extinctions to these vulnerable periods, proving how intimately our survival is tied to the core's hidden inferno. Modern technology lets us peek into this inaccessible realm. Seismic waves from earthquakes reveal the core's layered structure like a cosmic ultrasound, while supercomputers simulate its turbulent flows. Some experiments even recreate core conditions by crushing metal samples between diamond anvils while zapping them with lasers, a miniature version of the forces shaping our planet. The core's heat is slowly waning, though radioactive elements deplete over time, and the inner core grows as molten iron solidifies. In billions of years, Earth's engine may stall completely, its magnetic field fading as the planet cools into stillness. But for now, this subterranean powerhouse keeps continents dancing, volcanoes rumbling, and compasses pointing north, a reminder that the most vital part of our world is also the one we'll never see. Jupiter's moon Io is the solar system's unrelenting firebrand, a world where lava lakes churn at 1,300 degrees Celsius, hotter than most furnaces on Earth. Unlike the frozen landscapes of Europa or Titan, Io's surface is a cracked, sulfur-stained canvas of volcanic fury, dotted with hundreds of erupting vents that spew molten rock dozens of kilometers into space. This isn't the slow, oozing volcanism we're used to. It's a spectacle of celestial violence where lava flows stretch for hundreds of kilometers and volcanic plumes cast shadows across terrain that's constantly being remade. The key to Io's relentless activity lies in its tortured relationship with Jupiter. Locked in a gravitational tug-of-war with its massive parent planet and neighboring moons Europa and Ganymede, Io experiences tidal forces so intense they warp its very structure. Imagine kneading a ball of dough, except this dough is a moon the size of Earth's own, flexing and compressing by as much as 100 meters with each orbit. This friction generates enough heat to melt rock, fueling volcanic eruptions that dwarf anything on our planet. The lava here isn't the familiar basaltic flows of Hawaii. It's ultramafic silicate lava, so hot and fluid it behaves more like liquid metal than molten stone. Some of Io's most stunning features are its persistent lava lakes, cauldrons of bubbling rock kept in constant turmoil by tidal stresses. Loki Patera, the largest of these, spans over 200 kilometers and acts like a planetary-scale lava lamp, with crusts forming and collapsing in cycles that last months. When fresh magma breaks through, infrared telescopes can spot the incandescent glow from Earth, a beacon of geological unrest across the void. Other volcanoes, like Peel, erupt in curtains of lava that shoot tens of kilometers upward before freezing into glassy shards that rain back down, creating blackened plains of volcanic glass. The sheer scale of Io's eruptions defies earthly comparisons. While Mount Etna might spew a few thousand tons of material per second, Io's Tivashta volcano once ejected magma at a rate that would fill an Olympic swimming pool every 2 seconds. These eruptions paint the moon's surface in surreal hues: yellows and oranges from sulfur deposits, blacks from silicate lava, and eerie whites where sulfur dioxide frost settles in frigid regions between volcanic hotspots. The result is a world that looks more like a painter's palette than a planetary body, a place where chemistry and heat collaborate on a masterpiece of chaos. What makes Io particularly fascinating is how it challenges our definitions of habitability. While utterly hostile to life as we know it, this moon proves that geological activity isn't just about internal heat, it's about how a world interacts with its environment. The same tidal forces that keep Io's interior molten might also be at work on distant exoplanets, raising the possibility of volcanic worlds orbiting gas giants in other star systems. Every eruption, every lava lake, and every towering plume is a lesson in how energy flows through the cosmos, transforming dead rock into a dynamic, ever-changing landscape. Future missions like NASA proposed Io Volcano Observer aim to study this infernal moon up close, measuring the composition of its lavas and mapping the intricate dance between Jupiter's gravity and Io's molten interior. Until then, Io remains a testament to the universe's capacity for extremes, a place where the line between geology and astrophysics blurs, and where the quiet vacuum of space gives way to fireworks of liquid rock. It's a reminder that even in the coldest reaches of the solar system, heat finds a way to make its presence known violently, beautifully, and endlessly. White dwarfs are the glowing embers of dead stars' stellar corpses that burn at a staggering 100,000 degrees Celsius, hotter than many active stars in the galaxy. These dense remnants form when stars like our Sun exhaust their nuclear fuel, shedding their outer layers in a shimmering planetary nebula while their cores collapse into an Earth-sized sphere of degenerate matter. Despite their small size, white dwarfs pack a sun's worth of mass into a volume smaller than our planet, creating densities so extreme that a single sugar cube of their material would weigh as much as an elephant on Earth. The surface of a white dwarf isn't just hot. It's a seething, ionized ocean of carbon and oxygen atoms crushed under gravity's relentless grip. Unlike main sequence stars that generate heat through fusion, these stellar remnants shine from residual thermal energy, slowly radiating their unimaginable heat into space over billions of years. The process is like unplugging a red-hot iron. It doesn't cool instantly but gradually fades, its glow dimming as it loses energy. Some of the oldest white dwarfs in the universe have cooled to a mere 4,000 degrees, their light waning to a dull red before eventually crystallizing into ultra-dense cosmic diamonds. What makes white dwarfs especially fascinating is their relationship with time. They're celestial time capsules cooling so slowly that even the universe's first white dwarfs, born over 13 billion years ago, still retain surface temperatures high enough to be detected. Their gradual dimming provides astronomers with a unique clock to measure the age of our galaxy. By studying the coolest white dwarfs in a star cluster, scientists can estimate when those stars first formed, offering glimpses into the Milky Way's earliest epochs. Yet these ancient embers aren't always peaceful. In binary systems, white dwarfs can siphon material from companion stars, triggering periodic nova explosions, or, if they exceed a critical mass, cataclysmic supernova that outshine entire galaxies. The heat generated in these events briefly rivals their original stellar cores, a violent encore to their already extreme existence. Even in isolation, their intense gravity bends light around them, an effect predicted by Einstein and now used to study everything from dark matter to the universe's expansion. The final fate of a white dwarf is a slow fade to black. Over trillions of years, far longer than the current age of the universe, they'll cool to the ambient temperature of space, becoming cold, dark spheres of crystallized matter. Until then, they serve as cosmic lighthouses, their searing surfaces illuminating the physics of extreme density, gravity, and heat in ways no laboratory could replicate. From their violent births to their glacial deaths, white dwarfs prove that even in stellar afterlife, heat and light persist, rewriting the rules of what it means to be a star. At the heart of a dying star's final moments, temperatures spike to an almost incomprehensible 100 billion degrees Celsius, briefly making it the hottest spot in the entire observable universe. This is the fleeting inferno of a supernova's core collapse, where the sheer violence of gravitational energy converting into heat outstrips even the Sun's nuclear furnace by a factor of 10 million. For context, that's like comparing a birthday candle to the entire Earth being vaporized in an instant. In these critical seconds, the extreme conditions forge elements heavier than iron, gold, platinum, uranium, that ordinary stellar fusion could never produce, then catapults them into the cosmos in a shockwave of incandescent debris. The physics behind this is staggering. As the collapsing core rebounds, it creates a supersonic shockwave that rips through the star's outer layers, while neutrino particles, so numerous they could outnumber all the grains of sand on Earth, carry away 99% of the explosion's energy. The remaining 1% is enough to light up galaxies, heating the expanding debris to millions of degrees and illuminating it for weeks or months. It's this afterglow that we observe as a supernova, but the true spectacle happens invisibly, deep within the collapsing core, where atomic nuclei are hammered into heavier forms like cosmic anvils. Consider the gold in a wedding ring or the uranium fueling nuclear reactors. These atoms were born in such cataclysms. Ordinary fusion in stars can only create elements up to iron. Anything heavier requires the neutron-rich environment of a supernova's core, where rapid neutron capture, or the R process, a forces atomic nuclei to swell by gobbling up neutrons before decaying into stable heavy metals. Without these explosions scattering precious metals across space, Earth's crust would lack the elemental diversity that made complex chemistry and life itself possible. Supernovae aren't just destructive, they're the universe's ultimate alchemists. The 1987 supernova in the Large Magellanic Cloud offered proof, its spectrum revealing freshly synthesized strontium and other heavy elements. More recently, gravitational wave observatories detected colliding neutron stars, another R process site, confirming that the universe distributes its riches through violence. Even our bodies carry traces of these events. The iron in our blood and the calcium in our bones were once forged in stellar cores or their explosive deaths. Yet for all their brilliance, these temperatures are ephemeral. Within minutes, the core's heat dissipates as the shockwave propagates outward, leaving behind either a neutron star or black hole. The gold spun from this chaos may take millions of years to coalesce into new planets, but its origin story remains written in the searing physics of those first seconds. It's a reminder that the universe's most valuable creations often arise from its most extreme conditions, a fleeting fire that lights the dark with the seeds of worlds. Deep beneath the Swiss-French border, scientists briefly recreate a temperature not seen naturally since the first microseconds of the universe's existence, 5 trillion degrees Celsius. That's over 300,000 times hotter than the core of our Sun, achieved inside the Large Hadron Collider when heavy ions like lead nuclei collide at nearly light speed. These fleeting collisions don't just produce heat, they melt the very structure of matter itself, reducing protons and neutrons into their primordial components, a seething soup of free-flowing quarks and gluons known as quark-gluon plasma. For context, imagine taking every molecule in your body and dissolving them into their fundamental particles, erasing all boundaries between atoms until only an undifferentiated sea of quantum ingredients remains. That's the state of matter physicists believe filled the entire observable universe in its first 10 millionth of a second, before cooling allowed quarks to combine into the particles we recognize today. The LHC's detectors capture this plasma for mere fractions of a nanosecond, but that's enough to reveal astonishing behaviors, like near-perfect fluidity, where this superheated slurry flows with less resistance than liquid helium, defying expectations for something born in such extreme conditions. What makes these experiments revolutionary isn't just the record-breaking temperatures, it's how they mimic cosmic archaeology. By recreating quark-gluon plasma, scientists effectively turn back the universe's clock to a time before stars, planets, or even atoms existed. The plasma's properties hint at why matter eventually clumped into galaxies instead of annihilating completely with antimatter, a mystery central to our existence. Some theories suggest the plasma's fleeting existence might have tilted the scales in matter's favor during those critical early moments. The technical marvel lies in how researchers detect something so ephemeral. When quark-gluon plasma cools, it freezes into thousands of new particles that spray outward like cosmic shrapnel. Advanced detectors track these debris patterns, reconstructing the plasma's properties like forensic scientists analyzing a microscopic crime scene. Surprisingly, the plasma's behavior aligns with predictions from quantum chromodynamics, the theory governing quark interactions, validating decades of theoretical work while still leaving puzzles, like why certain high-energy collisions produce unexpected particle correlations. Beyond pure physics, these experiments have practical echoes. The same computational models used to simulate quark-gluon plasma now aid cancer therapy research, where understanding how energy deposits in dense matter helps target tumors more precisely. There's even speculative work suggesting quark-gluon states might exist inside neutron stars, meaning the LHC could be probing exotic astrophysics right here on Earth. As upgrades push the collider to even higher energies, each new experiment peels back another layer of the universe's infancy. The temperatures achieved here don't just break records, they illuminate the cosmic forge where the building blocks of reality first took shape, revealing how chaos and perfection once danced together in a firestorm beyond comprehension. Wolf-Rayet stars are the universe's dying fireworks, cosmic giants so ferociously hot they burn at 200,000 degrees Celsius, over 35 times hotter than our sun's surface. These rare stellar behemoths represent a star's final act before exploding in a supernova, spending just a few 100,000 years shedding their outer layers in supersonic winds that blast outward at nearly 9 million kilometers per hour. Imagine standing on a planet, if one could survive, where the sunlight isn't just blinding, but carries enough energy to strip away entire atmospheres with its fury. What makes these stars truly exceptional is how they rewrite their own fates. Unlike typical stars that gradually exhaust their hydrogen fuel, Wolf-Rayet stars have already torn off their outer hydrogen envelopes, exposing searing hot helium cores to space. This exposure triggers extreme nuclear reactions that fuse heavier elements like carbon, nitrogen, and oxygen at breakneck speeds, then catapults them into the cosmos through those relentless stellar winds. The result is a celestial foundry where the star effectively turns itself inside out, spewing the very elements needed for planets and life across the galaxy. The violence of this process sculpts space itself. Hubble images reveal intricate nebulas around Wolf-Rayet stars, their shapes twisted into glowing bubbles and bow shocks by the sheer force of those particle winds. One notable example is the Crescent Nebula, where a Wolf-Rayet star's outbursts have carved a structure spanning 25 light-years, its edges fluorescing as ejected elements collide with interstellar gas. These nebulas become cosmic graveyards and nurseries simultaneously, tombs for the dying star, but cradles for future solar systems enriched by its sacrifice. These stars don't just die quietly, they seed the universe with their remains. Spectroscopy shows their winds contain startling amounts of carbon dust, the same element that forms diamonds on Earth. In galaxies like the Milky Way, Wolf-Rayet stars may be responsible for up to half the carbon present, meaning the graphite in your pencil and the carbon in your DNA might trace back to such stellar cataclysms. Their winds also carry neon, magnesium, and silicon, elements that later coalesce into rocky planets and even the glass in your smartphone screen. Their end is as dramatic as their life. When a Wolf-Rayet star finally exhausts its nuclear fuel, it doesn't just explode, it detonates as a type Ib or Ike supernova, often leaving behind a black hole where moments earlier a star roared. Some may even produce gamma-ray bursts, the universe's most energetic explosions, capable of sterilizing entire galaxies if aimed wrong. Yet from this destruction comes creation, as the supernova scatters even heavier elements like gold and uranium into the void. Wolf-Rayet stars remind us that the universe thrives on cycles of destruction and rebirth. They're rare, just 500 are known in our galaxy, but their impact is universal. Every time you inhale oxygen or admire a gold ring, you're touching stardust forged in conditions so extreme they defy earthly logic, a legacy written in heat and light across the cosmos. Brown dwarfs occupy a cosmic gray zone too massive to be planets, yet too small to fully ignite as stars. These celestial oddballs simmer at around 1,700 degrees Celsius, a temperature that would vaporize steel yet falls far short of the million-degree infernos inside true stars. Imagine a world where the skies never truly darken, perpetually glowing a dull red from the object's residual heat, but never bright enough to sustain life as we know it. That's the realm of a brown dwarf, a failed star that couldn't muster the gravitational pressure needed to trigger sustained hydrogen fusion in its core. What sets them apart from gas giants like Jupiter is their origin story. While Jupiter formed from the leftovers of our solar system's protoplanetary disk, brown dwarfs collapse from their own interstellar gas clouds just like stars. They're born with the same raw materials but lack the mass to cross the critical threshold around 80 times Jupiter's mass where fusion kicks in. The result is an object that starts hot from gravitational contraction but gradually cools over billions of years, fading from a dim red ember to an almost invisible infrared whisper. Compared to main sequence stars, brown dwarfs are the cosmic underachievers. A small red dwarf star, the faintest true star, still burns at around 2,300 degrees Celsius, hot enough to sustain fusion and shine steadily for trillions of years. Brown dwarfs, by contrast, peak early. Their brief deuterium fusion phase, burning heavy hydrogen isotopes, might last a mere 100 million years before they resign themselves to a slow, uneventful cooling. Some older brown dwarfs discovered in recent years hover at temperatures comparable to a kitchen oven, their atmospheres swirling with exotic clouds of molten iron and sand like silicates. Yet these objects are far from boring. Their atmospheres defy categorization, exhibiting weather patterns stranger than any gas giants. Observations reveal violent storms with winds exceeding hurricane speeds, and some brown dwarfs show evidence of auroras without a star's magnetic field to power them, possibly generated by interactions with nearby planets. The spectral lines of their light reveal molecules like methane and water vapor, traits typically associated with planets, alongside titanium oxide seen in stars. This hybrid chemistry makes them invaluable laboratories for studying how cosmic objects blur the lines between categories. The discovery of brown dwarfs has forced astronomers to rethink their definitions. Before the 1990s, theorists debated whether such objects could exist at all. Now, thanks to infrared telescopes like WISE and Spitzer, we know they're surprisingly common, potentially outnumbering true stars in our galaxy. Some orbit alone in interstellar space, while others drift companionably near stars or even host their own planetary systems. One famous example, TRAPPIST-1 dim neighbor 2, mass J 23,062,928, hosts a family of rocky worlds, proving that even failed stars can foster complex cosmic neighborhoods. What makes brown dwarfs particularly fascinating is their longevity. While massive stars blaze out in supernova after a few million years and sun-like stars fade after billions, brown dwarfs will outlast them all. Their sluggish cooling means the smallest could still emit detectable heat long after every true star in the universe has burned out. In the distant future, these forgotten embers might be the only sources of warmth left in an otherwise dark and cooling cosmos, silent witnesses to the end of stellar glory. PSR J0437 4715 defies the stereotype of dead stars cooling quietly into oblivion. This pulsar's surface blazes at a staggering 1 million degrees Celsius despite being over 2,000 times older than human civilization. Most neutron stars gradually fade as they shed their birth heat, but PSR J0437 4715 bucks the trend, maintaining temperatures rivaling freshly formed stellar remnants. The secret lies in its frenetic spin, a celestial dynamo converting rotational energy into relentless heat through a process called spin-down heating. Discovered just 700 light-years from Earth, this millisecond pulsar whips around 174 times every second, its beam of radio waves sweeping past us like a cosmic lighthouse. Each rotation isn't just a display of stellar endurance, it's a friction-powered furnace. As the pulsar's magnetic field interacts with surrounding particles, it creates drag that slows the spin infinitesimally, a phenomenon known as spin-down. But that lost rotational energy doesn't vanish. It transforms into thermal energy, reheating the surface through a quantum mechanical dance between electrons and the star's crust. The physics at play here borders on alchemy. Pulsars like J0437 4715 are born from supernova explosions, their cores compressed into a soup of neutrons so dense that atomic structures collapse. Ordinarily, these remnants should cool rapidly, but rapid spinners rewrite the rules. Their interiors harbor superfluid neutrons that generate vortices, whirlpools of quantum turbulence. When these vortices interact with the star's solid crust, they convert breaking energy into heat with near-perfect efficiency. It's as if the pulsar has an internal friction heater, its spin acting like winding a cosmic watch that never fully unwinds. What makes J04374715 especially fascinating is its dual identity. Not only is it one of the hottest known pulsars, but it's also the nearest millisecond pulsar to Earth, giving astronomers an unrivaled laboratory for testing neutron star physics. Observations reveal its surface isn't uniformly hot, magnetic poles blaze brighter, while equatorial regions show subtle temperature variations that hint at internal heat distribution we're only beginning to map. Some theories suggest its heat might even stem from a hidden companion star, whose stolen mass could be raining onto the pulsar and reigniting nuclear reactions at the surface. The implications stretch beyond stellar curiosities. Pulsar timing arrays use J04374715's precise rotations to hunt for gravitational waves, its stability acting like a cosmic metronome. Meanwhile, its extreme heat challenges assumptions about how neutron stars age. If spin-down can keep a stellar corpse burning for billions of years, it raises tantalizing questions about other old pulsars. Could some appear artificially young, their surfaces deceptively hot from hidden reservoirs of rotational energy? This pulsar's defiance of cosmic decay teaches us that death in space isn't always cold. Sometimes it's a slow burn, a testament to how the universe repurposes energy in ways that continually surprise us. From gravitational wave detection to quantum superfluids, J04374715 proves that even the oldest stellar remnants can be the most illuminating. Hypernovas take stellar destruction to an entirely new level. When one erupts, temperatures can spike to an incomprehensible 1,000 billion degrees Celsius, making even a supernova's core seem almost lukewarm by comparison. These aren't just bigger versions of standard supernovas, they're fundamentally different beasts. While a typical supernova marks the death of a star between 8 and 20 solar masses, hypernovas occur when massive stars, think 30 times the Sun's mass or more, collapse into black holes with such force that they unleash tightly focused jets of energy moving at nearly the speed of light. What sets hypernovas apart is their connection to gamma-ray bursts, the most energetic electromagnetic events since the Big Bang. In a hypernova, those relativistic jets piercing through the dying star's outer layers concentrate their energy into twin beams so intense that, if one happened within a few thousand light-years of Earth, it could strip our ozone layer and trigger mass extinctions. The temperature within these beams, briefly exceeding 1 trillion degrees, creates conditions where matter and antimatter particles spontaneously form and annihilate in violent bursts of gamma radiation. The physics behind these events reads like cosmic science fiction. As the star's core collapses, it doesn't just form a neutron star, it implodes directly into a black hole, spinning so fast that it warps space-time around it. This rotation powers magnetic fields strong enough to accelerate particles to nearly light speed, funneling them into those deadly jets. The process converts roughly the Sun's entire mass into pure energy within seconds, releasing more brightness than our entire galaxy for a fleeting moment. We've witnessed hypernovas indirectly through their gamma-ray signatures. The famous JAB 080319b, detected in 2008, originated from a hypernova 7.5 billion light-years away, yet for 30 seconds, its afterglow outshone the combined light of every star in the Milky Way. Such bursts serve as cosmic lighthouses, their light carrying clues about the early universe's chemical composition and the birth rates of massive stars in distant galaxies. Interestingly, hypernovas may be the cosmic forges responsible for heavy elements like gold and platinum. Traditional supernovas can't explain the abundance of these metals in the universe. Their R-process neutron capture happens too slowly. But hypernovas, with their extreme neutron densities and temperatures, could be the true cosmic mints, stamping out precious elements in their apocalyptic deaths. Every gold necklace or uranium fuel rod on Earth might owe its existence to these brief, unimaginably violent events scattered across cosmic history. The rarity of hypernovas adds to their mystique. For every 100 supernovas, only 1 or 2 reach hypernova status. Their formation requires perfect conditions, a rapidly rotating, metal-poor massive star that avoids shedding too much mass before collapse. In modern galaxies like ours, where stars are rich in heavier elements, true hypernovas may be vanishingly scarce. But in the early universe, where giant pristine stars were common, they might have lit up the cosmic dark like fireworks, seeding galaxies with the elements and radiation that shaped everything that followed. Ongoing missions like the James Webb Space Telescope and gravitational wave observatories offer new ways to study these events. By combining gamma-ray data with neutrino detections and space-time ripples, scientists hope to unravel how hypernovas influence galactic evolution and whether their lingering radiation could have played a role in kickstarting life's building blocks billions of years later. For now, they remain nature's ultimate particle accelerators, brief glimpses into physics so extreme it challenges our very understanding of energy, matter, and the limits of cosmic violence. Quasars are the universe's ultimate powerhouses, beacons so bright they outshine entire galaxies, fueled by black holes with appetites so insatiable they could devour stars like snacks. But the real spectacle isn't just the black hole itself, it's the swirling maelstrom of superheated gas around it, screaming toward oblivion at nearly light speed. This cosmic carousel, called an accretion disk, generates temperatures exceeding 10 trillion degrees Celsius, so extreme that even atomic nuclei can't hold together, dissolving into a seething plasma of quarks and gluons. The physics behind this heat is as mesmerizing as it is violent. As gas spirals inward, particles collide with such ferocity that friction alone becomes a nuclear furnace. Picture 2 jets screaming through the sky at full throttle, their wings scraping against each other. Now scale that energy up to celestial proportions, with entire suns worth of material grinding together in a gravitational vice. The resulting heat doesn't just glow, it blasts X-rays and gamma rays with enough energy to sterilize planets light years away. Some quasars flicker in brightness over mere days, proving their accretion disks are smaller than our solar system yet pump out more energy than a trillion suns. Quasars also defy expectations with their sheer diversity. Some, like the record holder J03131806, existed when the universe was barely 670 million years old, far too young by cosmic standards to grow such monstrous black holes. Their existence suggests black holes might form through exotic channels, like direct collapse of giant gas clouds skipping the star stage entirely. Others, like 3C273, appear deceptively star-like in telescopes despite being 2 billion light-years away, their brilliance making them landmarks across the cosmos. What makes these objects especially fascinating is their double role as destroyers and creators. The same accretion disks that vaporize matter also funnel some material into relativistic jets, columns of plasma fired outward at near light speed, carving bubbles in intergalactic space that persist for millions of years. These jets can stretch millions of light years, making them the largest structures in the universe sculpted by a single object. Ironically, the radiation and shock waves from quasars might actually trigger star formation in distant gas clouds, proving even cosmic monsters can inadvertently nurture life. Observing quasars is like looking back in time. Their light often carries fingerprints of ancient gas clouds they've illuminated along the way. The Very Large Telescope has detected quasar beams piercing primordial hydrogen from the cosmic dawn, revealing how the early universe transitioned from opaque fog to transparent space. Meanwhile, gravitational lensing, where foreground galaxies bend quasar light into multiple images, lets astronomers use them as celestial microscopes, magnifying even fainter objects behind them. Yet for all their fury, quasars are fleeting. As black holes exhaust nearby fuel, their accretion disks dwindle, leaving behind dormant giants like the one at our galaxy's core. The brightest quasars likely burned out billions of years ago, their light still traveling toward us as ghostly echoes of an era when the universe was younger, denser, and far more violent. They remind us that the cosmos thrives on cycles where today's quiet galaxies were once the scenes of the most extreme physics imaginable, written in fire across the void. The universe saves its most extreme temperatures not for stars or supernova, but for the narrow, focused beams of destruction screaming from black holes' relativistic jets, where particles racing at over 99.9% the speed of light create theoretical temperatures nearing 100 trillion degrees Celsius. These aren't just hotspots, they're cosmic blowtorches capable of punching through entire galaxies, their heat so intense it defies the very laws of physics as we know them. At the heart of this phenomenon lies the black hole's accretion disk, a swirling vortex of doomed matter heating up to millions of degrees. But as particles spiral inward, some get caught in the black hole's powerful magnetic fields and are catapulted outward along its poles at nearly light speed. The energy here is so concentrated that collisions between these particles don't just release heat, they tear apart the fabric of quantum fields, momentarily producing temperatures rivaling the universe's first microseconds after the Big Bang. What makes these temperatures theoretical is their fleeting, chaotic nature. We can't measure them directly, no thermometer could survive, but physics tells us that when particles moving at such extreme velocities collide, their kinetic energy converts into heat so vast it briefly mimics conditions we've only recreated in particle colliders for fractions of a second. In essence, these jets are nature's own Large Hadron Collider, but operating on scales that dwarf human engineering. The consequences of such heat are mind-bending. Protons and neutrons melt into quark-gluon plasma, the same primordial soup that filled the early universe. Photons trapped in this maelstrom gain so much energy they shift into deadly gamma rays. Even time distorts here. A minute in the jet's reference frame could equate to centuries outside it, thanks to relativistic effects. Astronomers study these jets through their aftereffects. When they slam into interstellar gas, they create shock waves visible across millions of light years, like the famous M87 jet captured by the Event Horizon Telescope. Some jets, like those from Quasar 3C273, stretch over 200,000 light-years, twice the diameter of our Milky Way, proving that black holes don't just consume matter, they reshape the cosmos around them with these focused beams of unimaginable energy. Yet for all their destructive power, these jets might also be cosmic architects. Their radiation could trigger star formation in distant gas clouds, while the heavy elements forged in their wakes may seed future planets. Even Earth's history might bear their fingerprints. Some theories suggest a nearby jet's gamma rays could have sparked past extinction events. In the end, relativistic jets are a reminder that the universe's most extreme temperatures don't linger in vast explosions, but in these precise, almost surgical displays of power where nature proves that heat, focused and accelerated, can become something far more than just a number on a scale. The Planck temperature, 1.4 times 10 to the 32 degrees Celsius, isn't just another extreme number in physics. It represents the absolute upper limit of heat, a boundary so extreme that our current understanding of reality itself breaks down. To grasp the sheer scale of this temperature, imagine taking all the energy released by every star, supernova, and quasar in the observable universe and compressing it into a single microscopic point. That's the level of intensity we're talking about, a heat so incomprehensible that particles wouldn't just vibrate wildly. They'd reach energy levels where gravity, quantum mechanics, and all known forces merge into a single, indistinguishable blur. This isn't theoretical fantasy. The universe actually reached this temperature, if only for the tiniest fraction of a second during the Planck epoch, the first sliver of time after the Big Bang. For 10 to the minus 43 seconds, everything that would become galaxies, stars, and even the atoms in your body existed as a seething, unfathomably dense singularity. At these energies, matter and energy were indistinguishable. Space-time itself flickered in and out of existence, and the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, all-encompassing interaction. It's the only moment in cosmic history where temperature wasn't just a measure of heat, but a signature of the universe's very structure rewriting itself. What makes the Planck temperature especially mind-bending is how it challenges our tools of measurement. Normally, temperature reflects the average motion of particles, but at this extreme, particles as we know them cease to exist. Quantum fluctuations would be so violent that virtual particles, which usually pop in and out of existence fleetingly, would become permanent fixtures, warping the fabric of reality. Even black holes, the universe's most efficient energy converters, would evaporate instantly under these conditions, their mass dissolving into pure radiation faster than the blink of an eye. Physicists sometimes describe the Planck scale as nature's resolution limit, the point where space and time stop being smooth and continuous, instead becoming grainy, like a cosmic version of pixelation. Attempting to probe temperatures beyond this would be like trying to zoom in beyond the smallest dot on a digital image. The very concept of hotter loses meaning. It's not that we lack the technology to reach these extremes, it's that the laws of physics as we know them provide no framework for what beyond would even look like. The legacy of this primordial heat still echoes today. The universe's expansion and cooling from that initial inferno created the uneven distribution of matter we see in galaxy clusters, the cosmic microwave background's faint glow, and even the very elements that compose our bodies. In a way, every atom, every star, and every life form is a relic of that first unimaginable temperature, stretched and transformed across billions of years. The Planck temperature isn't just a record, it's the universe's birth certificate, written in energy so extreme it defies description, yet set the stage for everything that followed. Lava worlds redefine the very concept of extreme planets. Imagine a place where the ground itself is an endless, churning ocean of molten rock, with temperatures soaring to 2,500 degrees Celsius. Kelt 9b stands as the poster child for these blistering hellscapes, an exoplanet so close to its star that its dayside temperature rivals that of some small stars. This isn't just a hot planet, it's a world where metals like iron and titanium exist as vapor in the atmosphere, raining back down as molten droplets in a perpetual cycle of evaporation and condensation. The physics behind these molten giants is as fascinating as it is terrifying. Tidal locking ensures one side of the planet permanently faces its star, creating a dayside so scorching that whole rock formations sublimate directly from solid to gas. Meanwhile, the night side, though relatively cooler, still simmers at temperatures that would melt steel, with sluggish lava flows creeping through the darkness like glowing black tar. The temperature gradient between these two hemispheres generates supersonic winds, screaming at speeds over 5,000 kilometers per hour, carrying vaporized rock from the dayside to the night side where it condenses and falls as lava rain. Kelt 9b star adds another layer of brutality. It's a blue-white beast nearly twice as hot as our Sun, bombarding the planet with ultraviolet radiation so intense that the exoplanet's atmosphere is literally boiling away into space. Observations suggest it's losing around 10 billion tons of material every second, enough to form a comet-like tail of vaporized metals stretching far into the void. In a few 100 million years, this relentless stellar assault might strip the planet down to nothing but a scorched core, a grim testament to the violent relationship between star and planet. What makes lava worlds particularly intriguing is how they blur the line between planet and star. Some, like Co-Rho T7b, exhibit such extreme volcanism that their surfaces might be resurfaced entirely by lava eruptions every few centuries. Others, like WASP 76b, have atmospheres so hot they contain ionized calcium, an element normally found only in stellar spectra. These aren't just dead rocks, they're dynamic, evolving worlds where geology unfolds at a pace and scale unimaginable on Earth. Future telescopes like the James Webb Space Telescope aim to study these planets in unprecedented detail, analyzing the chemical composition of their molten atmospheres for clues about planetary formation and destruction. Some theories suggest lava worlds could be the remnants of failed gas giants, their atmospheres stripped away to expose the molten cores beneath. Others propose they might represent a phase in planetary evolution, a fiery adolescence that some worlds pass through before cooling into something more familiar. The existence of these molten giants challenges our definitions of habitability and planetary diversity. While utterly hostile to life as we know it, they remind us that the universe thrives on extremes, that for every Earth-like world, there might be a dozen others where the very ground is fire, the sky rains metal, and the night never falls. They're cosmic crucibles, forging new questions about where planets end and stars begin. Deep within our sun's core, where temperatures soar to an unimaginable 15 million degrees Celsius, a relentless nuclear furnace powers every sunrise, every gust of wind, and every heartbeat of life on Earth. This isn't just heat, it's a maelstrom of atomic collisions so intense that hydrogen nuclei overcome their natural repulsion, fusing into helium in a process that releases energy on a scale defying comprehension. Every second, 600 million tons of hydrogen vanish in this stellar crucible, converted into 596 million tons of helium, with the missing 4 million tons transformed directly into pure energy, enough to power human civilization for 500,000 years. The engine driving this cosmic alchemy is called the proton-proton chain. It begins when two hydrogen nuclei single protons collide with such force that one flips its quantum spin, allowing the weak nuclear force to bind them together. This delicate dance creates deuterium, a heavy hydrogen isotope, while spitting out a positron and a neutrino. Next, this deuterium atom snags another proton, forming helium-3 and releasing a burst of gamma rays. Finally, two helium-3 nuclei crash together, creating stable helium-4 while ejecting two leftover protons back into the reaction pool. Each step is absurdly unlikely under earthly conditions. Protons would need to wait billions of years for quantum tunneling to make fusion happen. But the sun's crushing gravity and extreme heat compress these events into milliseconds. Neutrinos, the ghostly byproducts of these reactions, tell a story of their own. Nearly 100 billion solar neutrinos pass through your thumbnail every second, traveling at near light speed after escaping the sun's core unimpeded. Unlike photons, which take tens of thousands of years to zigzag their way through the sun's dense interior before racing to Earth in 8 minutes, neutrinos bolt straight out, offering scientists a real-time snapshot of fusion activity. Early neutrino detectors in the 1960s initially captured only a third of the predicted flux, sparking a decades-long mystery: the solution. Neutrinos oscillate between three flavors: electron, muon, and tau as they travel, meaning early instruments missed 2/3 of them. This revelation reshaped particle physics, proving neutrinos have mass and earning researchers the Nobel Prize. The energy produced in this core doesn't just vanish into space, it embarks on an epic journey. gamma rays born from fusion bounce endlessly in the radiative zone, taking up to 200,000 years to travel 500,000 kilometers to the convective zone, where superheated plasma carries them the final 80% of the way to the surface in mere weeks. By the time this energy escapes as sunlight, it's been downgraded from lethal gamma radiation to harmless visible light, a testament to the sun's ability to temper its own fury. Yet the sun's core isn't uniform. Helium ash accumulates at its center, gradually increasing density and temperature, a slow burn that over billions of years will make our star swell into a red giant. Current models suggest the core's temperature has risen by 20% since the sun's birth 4.6 billion years ago, a subtle but inexorable shift that will eventually render Earth uninhabitable. This relentless fusion reactor is more than just a power source. It's the universe's most precise scale. The balance between gravity's inward crush and fusion's outward push keeps the sun stable to within 1% over millennia. Even a slight imbalance would trigger catastrophic expansion or collapse, proving that stellar cores aren't just hot, they're perfect cosmic regulators, fine-tuned by physics to burn steadily for billions of years. Every leaf's photosynthesis, every solar panel's hum, and every sunset's glow trace back to this crucible where matter becomes light, and the ordinary transforms into the extraordinary. By studying these processes, we're not just unraveling stellar mechanics, we're learning to replicate them. Experimental fusion reactors like ITER aim to harness the proton-proton chain on Earth, potentially unlocking an era of clean energy. While we've yet to achieve net energy gain, each breakthrough brings us closer to taming the fires that have illuminated the cosmos since the first stars flickered to life. The sun's core isn't merely the heart of our solar system, it's a blueprint for humanity's future among the stars. From the frozen silence of absolute zero to the universe-shattering fury of the Planck temperature, we've journeyed across a cosmic spectrum of heat and cold so extreme it bends reality itself. Think about that for a moment. Everything we know, from the ice on Pluto to the heart of a supernova, exists within this staggering range. At one end, atoms nearly stop moving entirely, surrendering to quantum whispers. At the other, matter itself dissolves into a seething chaos where the laws of physics as we understand them simply break. These aren't just numbers on a scale, they're the invisible architects shaping stars, planets, and even the building blocks of life. Consider how these extremes touch everything. The brutal cold of the Boomerang Nebula teaches us how dying stars sculpt space with their final breaths. The sun's core, a relentless fusion reactor, reminds us that light and warmth come from violence on an unimaginable scale. Even the fleeting trillion-degree heat of quark-gluon plasma in particle colliders echoes the universe's fiery birth. Every extreme temperature tells a story of creation, destruction, and the delicate balances that make our existence possible. Without the cold of interstellar space, nebulae couldn't collapse into stars. Without the heat of stellar cores, atoms heavier than hydrogen would never have formed. We are quite literally the products of these extremes. So which fact left you speechless? Was it lightning hotter than the sun's surface, or the eerie superconductors that float magnets in midair? Maybe it was the way neutron stars, colder than Pluto in some ways yet burning at 1,000,000 degrees in others, defy all expectations. The universe thrives on these contradictions, pushing matter and energy to their limits, and then beyond. If these wonders ignited your curiosity, you're not alone. The cosmos has endless surprises waiting, from black holes that bend time to exoplanets where it rains glass. Hit subscribe to keep exploring with us. Every click is a step deeper into the greatest mysteries of space. And don't forget to drop a comment below. What temperature shocked you the most? Was it the icy grip of absolute zero or the Planck firestorm? The universe is stranger than we can imagine, and together we're just getting started.